Welcome to Phantastic Physics. Today we're going to analyze what's called a truss structure. Typically you'll see trusses as a bridge. You may have walked across a truss bridge or driven a car across one. They're very common. You also tend to see truss structures in buildings that are, very wide floor prints, and so you need some sort of support near the ceiling, and that ceiling support might take the shape of a truss structure. And basically what a truss looks like is it's going to have a bunch of diagonal members, and these diagonal members are going to be either in tension, which means they're going to be either pulled apart, or they're in compression, which means they're being squeezed together. And so every member will be in either tension or compression, or in some cases there are what are called zero force members. So these are members that actually have no force. They're actually not bearing any load under specific circumstances, and we'll talk about that later. So here's an example of a truss bridge, a very simple one. And so I gave it dimensions of 10 feet by 10 feet. So the vertical dimension is 10 feet, and then each of these horizontal members is also 10 feet, so a total of 20 horizontally. And so the members are the diagonal elements themselves. So if you were to count how many members are in this bridge, we could say 1, 2, 3, 4, 5, 6, 7. So 7 members. And the joints are places where 2 or more members come together and are connected. So if we were to count the joints here, we would say 1, 2, 3, 4, 5 joints. And there's also something else, which is known as a reaction, R-E-A-C-T-I-O-N. So before I can explain any further, I need to help us understand what a reaction force actually is. So let's start by looking at the supports. So if you look at my bridge, there's a support over on the left side and a support on the right side. And the supports are what hold up the bridge, right? It could be sitting on a column, it could be sitting on something, but basically if this is all water in the span here underneath, then maybe it's supported on the edges where land is, right? And so there's really 2 types of supports that I'm going to talk about in today's lesson. And so on the left, my support on that side is what's called a roller support. And a roller support is typically modeled as a circle, like a wheel, sitting on the ground, okay? So if a bridge is supported on a roller support, that means it's free to move in one direction. So in the case of this roller, it actually has free movement in the horizontal direction. And because it's free to move in the horizontal direction, we say that there's something called a reaction force that's preventing it from moving in the vertical direction. So there's something called R, a reaction, which means that, like, if I came and I started pulling up on this bridge with some force, some external force, something has to stop this roller from moving up and down, right? So in that case, there would actually be a downward reaction force that's resisting this upward force. But if somebody came in and started pushing down on this bridge, so they pushed down with an external force, well, now that reaction force has to push up, because if there wasn't a reaction there, then this bridge would actually start falling, right? And so there has to be some kind of force at that support. That's what we call a reaction force. So remember, a roller only has a vertical reaction force because it is free to roll left and right, okay? And so the other type of support is what we call a pin support. And that's the one I've drawn on the bottom right here. So a pin support is usually drawn as a triangle sitting on the ground or some kind of surface, right? And so a pin support you could think of as a hinge, right? So a door, when you open a door, how does a door work? It actually freely rotates on a hinge, right? So, and actually, same is true of my elbow here. So my forearm can rotate around the hinge, but for a pin connection, it's not free to move left and right like a roller is, and it's also not free to roll to move up and down in the vertical direction. So a pin support allows the entire bridge to rotate around that support. And actually, if there was nothing over on the left side, so imagine there's no support there, and I push down on this bridge, it's true that the entire bridge would rotate around this pin support. So the only thing stopping that rotation, of course, is having some other support over there. So a pin support, like I said, it allows for rotation, but it does not allow for vertical or horizontal movement. And because a pin support is restricting 2 directions of motion, we say it has a vertical reaction. You could call that RY, a reaction in the vertical direction, and a horizontal reaction, which you could call RX. So again, imagine I come over and I push down on this bridge with some kind of external force. Well, there has to be some kind of reaction force at that pin connection that is pushing back up and preventing the bridge from sinking, right? Or likewise, if I came and I grabbed this edge of the bridge and I started pulling it leftward with the force, there has to be some kind of reaction force at this pin, which would be pulling it back to the right. Because if I just pull the bridge leftward and it starts moving, that would not be good. And so it's prevented from moving by this reaction force here at the pin. So now going back to my overall bridge structure, you can see I have a total of 3 reaction forces, right? But before I label them, let's go ahead and label each of my joints here. So I'm going to label them A, B, C, D, and E. And so I like to label my joints counterclockwise, but it doesn't really matter as long as you're consistent in your calculations. So I have joints A, B, C, D, and E. And that means my reaction forces that are occurring here is, remember, there's one vertical reaction at A. So I'm going to call that RA, reaction force at point A. And I'm going to assume that that reaction force is acting in the upward direction. Of course, we'll see later through our calculations whether that's true. It might be in the downward direction. And over at joint C, remember that's a pin connection, so it's going to have one vertical reaction force, which I'm going to call, let's call this RCY. So it's a reaction force at C in the Y direction. And we also have a horizontal reaction force, which I'm going to call RCX. So a reaction force at point C in the X direction. Now, again, I'm assuming these reactions are up and to the right. Once we do the calculations, we'll see whether that's true or not. They might be downward and to the left. Okay, so now I've gone ahead and added some external forces to our bridge, because without an external load, there's really going to be no compression or tension in any of the members, and there would be nothing to solve for. So I put a 1,000-pound force right at joint E, pushing down at joint E. I have a 3,000-pound force pushing down on joint D, and I have a 4,000-pound force here pulling down on joint B. Now, before I run through the calculations, there are some major assumptions we're making for the sake of simplifying this problem. And if we didn't make the following assumptions, solving for this real bridge would be significantly harder, and we may need to rely on computer software to do that for us. But if we make these assumptions, we can do these calculations by hand. So the first assumption is all of my external forces are happening directly at a joint. Now, in real life, of course, these forces could happen anywhere on this member or this member. Anywhere on this bridge, you could have an external force, but we're saying those forces are only acting exactly at a joint, okay? The second assumption is that they're point loads, which means that they're single forces concentrated on single points. Rather than having a distributed force where I might say, oh, there's 100 pounds per foot all across this member, we're saying the force is concentrated in one spot, okay? The third assumption is that these joints, so joints A, B, C, D, and E, they're being idealized as frictionless hinges. So just like we said that the pin connection at point C is a hinge, we're saying the same thing about all of these joints, that the way that they're connected together is not rigid, like, you know, a good bolting job or a good welding job where they're stuck and there's no rotation. We're assuming that they're the opposite of that they're free to rotate, that this is sort of a hinge connection. They're all coming together sort of like a door hinge. And the only thing stopping it from rotating there is all these members holding everything in place, okay? That's going to simplify our calculations a lot. The last assumption we're making is that all of these members are made of exactly the same material with the same characteristics, the same stiffness, everything's the same about them, and their cross-sectional areas and their shapes are all the same. So if these are rectangular members, they're all rectangles and they all have the same dimensions, okay? So those are our assumptions, and now we're ready to get started with the calculations. Okay, so now that we've identified our assumptions for solving this bridge, we're ready to actually start finding the answers, okay? Now, the first thing we have to do is identify the conditions known as static equilibrium. And there's really 3 equations of static equilibrium. So I'm going to write them on the board and then I'm going to explain them, okay? The first condition of static equilibrium is that the sum of all forces in the x direction must equal 0. So this symbol here, this is a Greek symbol for sum. We use it as a notation that means adding things together. So the sum of all forces in the x direction should add up to 0. That means that all of the forces acting in the horizontal direction, if they don't add up to zero, if they add up to something that's not zero, this bridge would actually start accelerating in some direction. And there's nothing worse than driving across a bridge that's actually accelerating with your car. We don't want that. So all of these forces have to add up to zero. The second condition of static equilibrium is that the sum of all forces in the y direction should also equal zero. So if I added up all my y forces, the vertical forces, if they don't add up to zero, that means we have a bridge that's either flying or sinking, right? And we can't have that. So we need our bridge to be steady, not accelerating in the x direction or in the y direction. So it must satisfy both of these conditions. The third condition is that the sum of all moments should equal zero. And so to understand this, we first have to understand what is a moment. So this M stands for moment. And a moment in engineering is what physicists would call torque. So moment and torque are used interchangeably. They're basically a rotational force. So for example, if you have a bolt that's stuck in something and you take a wrench and you try to turn this bolt, let's say this bolt has a distance of 8 inches from here to here. And let's say you apply a force of 10 pounds in the downward direction at the end of this wrench. So you're trying to turn this bolt by basically pushing downward. Well, we would say that the moment, or if you will, torque, on this bolt is equal to, so moment is equal to force times distance. So it would be the force that you apply times the distance to that bolt. So here it would be 10 pounds times 8 inches, and that would give you 80 pound-inches. So the units of moment are going to be a unit of force times a unit of distance, because it's a force times a distance. Now, the key thing for moments or torques is that the force has to be perpendicular to the distance. So if you applied a force of, let's say, 50 pounds directly to the left, so right along this line of action to the bolt, what would be the total moment applied to this bolt? And if you guessed 0, you would be correct. So this is actually not applying any rotation here, because the force is not causing this bolt to rotate. There is no perpendicular distance. So let me give you an example of what that would look like. If I redraw my wrench, so some wrenches, they look like this. This is called an L-shaped wrench. And let's say this wrench has an 8-inch dimension here and a 4-inch dimension here. And I take this same 50-pound force, and instead of applying it here, I apply it up here. Well, now did I apply a moment to this wrench or to this bolt? And if I did, can we calculate it? The answer is yes. So now there's a 50-pound force and there's a 4-inch perpendicular distance, right? So if the force is horizontal, the distance is vertical. It's the vertical distance between this force and where this bolt is, and that is 4 inches. So we have a moment of 50 pounds times 4 inches, and that gives us 200 pound-inches, right? And so you can see that to create any sort of rotation, you have to have a force and you have to have a distance that's perpendicular to that force. So if your force is horizontal, the distance is vertical, or in this case, if I applied the force vertically, then I would use the horizontal distance, okay? So going back to this static equilibrium condition, this means that if I add up all the rotational force on this bridge, it should come out to be 0, because think about it, do we want a bridge to be rotating in space when you're trying to drive on it? Of course not. So there shouldn't be any net X force in the X direction. There should be no net force in the Y direction. And there should be no net rotation on this bridge, so that it's a perfectly still bridge that's not trying to scare people on it. So now that we've established the 3 conditions of static equilibrium that we need in order to solve for this problem, we now need to establish something called static determinacy. And this basically means can we determine the actual tension and compression in these truss bridge members using our three equations of static equilibrium? If we can, then we're ready to proceed and solve. But if our bridge is statically indeterminate, that means we can't solve it using these three equations, and we're going to need more advanced methods that you would find at a upper division level college course, okay? So to determine static determinacy, to determine whether we can solve this bridge with these equations, we have to check that the number of unknowns in this bridge that we're solving for is less than or equal to the number of knowns. So what does that mean? Well, where are our unknowns? Where do those come from? Well, every member is an unknown force, right? So how many members do we have? 1, 2, 3, 4, 5, 6, 7. So the unknowns come from the members. And remember, we have 7 members in our truss, 7 unknown tension and compression values. But they also come from the reaction forces. We have how many unknown reactions? 1, 2, 3. Remember, we have RA, RCY, and RCX. So we got 3 more unknowns from our 3 unknown reaction forces. And remember, this has to be less than or equal to the number of knowns. Well, how many knowns do we have? Well, it's actually each joint, you get access to 2 of these equations, because remember, these joints are frictionless hinges, so there is no rotational force at the joints. There's no force stopping them from rotating, which means we don't get access to this third equation. And at every joint, when we start analyzing these joints later, we'll be able to check that the sum of the forces in the X is 0 and that the sum of the forces in the Y is 0. So because we have 2 equations at each joint, we have 1, 2, 3, 4, 5 joints. So 2 equations at each joint is the number of knowns that we have at our disposal, the number of equations. And so 2 times 5 gives us 10. And so what we're checking is that the number of members plus the number of reaction forces, or in this case 7 plus 3, 10, is less than or equal to 2 times the number of joints, which is 2 times 5, which in this case is 10. And so because our left side is less than or equal to our right side, we can say, yes, this bridge is statically determinate and we're able to solve it. Now, there is one more condition we have to watch out for, which is if we got 9 over here, and so we know that the number of unknowns is actually less than the number of knowns. Well, technically our bridge would be statically determinate, meaning that we could actually solve for it in this problem. The problem with this is when your number of unknowns is actually less than your number of knowns, you have what's called an unstable bridge. So the bridge would be on imminent verge of collapsing. This would actually not be desirable. So we would want to redesign our bridge so that the number of knowns is exactly equal to the number of unknowns. And that way we can say our bridge is both statically determinate, meaning we can solve it with these equations, and it's perfectly stable, meaning it's not going to collapse imminently. So now we're ready to start analyzing this bridge, and the first thing that we're going to do is actually solve for these 3 unknown reaction forces. So we actually need to figure out what those 3 reactions are before we're able to figure out what these internal truss member forces are, whether they're in tension or compression. And so remember, we have 3 equations of equilibrium. Some of the forces in the Y direction should equal 0, some of the forces in the X direction equal 0, and the sum of all moments or rotational forces should add up to 0. And I'm just going to tell you that the easiest way to solve this is to do the sum of the moments first. So we'll start with this condition. And actually, where am I going to take the sum of all moments around? So we remember a moment is a rotation around some point. And my advice is always pick the support that has 2 unknown reactions and take the moment around that. So I'm going to say the sum of all moments around point C equals 0. And technically you could pick any point on this bridge and the total moment or rotation around that point should add up to 0. But there is a reason I'm picking point C, and you'll see soon enough why that is, okay? So now we have to figure out what are all the forces that are causing moments around point C. So let's start by looking at this 1,000 pound force. This force way over here, imagine if I disconnected point A so that this bridge was free to rotate, and I pushed down on joint E with this 1,000 pound force, you can imagine that the whole bridge would start to rotate around point C. So what I'm saying is this 1,000 pound force is going to cause a rotation around point C, okay? So it creates a moment. So that's the first cause of a moment. So we're going to say 1,000 pounds. Now remember, this is a downward force, so we have to figure out what's the horizontal distance away from point C, because every vertical force should have a horizontal distance, right? And so if you think about it, joint E is halfway between this member, so that would be 5 feet, and then there's another 10 feet. So the total horizontal distance from this 1,000 pound force to joint C is actually 15 feet in the horizontal direction. So we would say we have 1,000 pounds that's 15 feet away, and that creates a moment of 1,000 times 15. That's a rotational force around point C equal to the product of the force and the distance, okay? And so what's the second source of moment around point C? That would be this 4,000 pound force. And that one's easy because you can very clearly see that is 10 feet away from point C. So we have another force of 4,000 pounds times 15 feet. Times 10 feet. So we have a second moment created that is equal to this force times this distance, and that's causing rotation around joint C. The last force is this 3,000 pound force. And how far away is this force from joint C? Well, remember, it's horizontally speaking, so it's 5 feet away, or half this member away from joint C. So we would say times 5 feet. And there's actually one more force that I haven't pointed out yet. And remember, there's that reaction force at point A. And this reaction force, again, if we disconnected this support over here, this reaction force would cause a rotation in the clockwise direction. It would push the entire bridge up and around the joint C if it was free to rotate. And so that's creating another moment that is 20 feet away from the joint C. So we would say there's also reaction A that's 20 feet away. And I am calling this moment a negative moment because all the other rotations caused by these forces were causing counterclockwise rotation, which is what we call positive rotation. But reaction A is a force that's creating a clockwise rotation, so it's in the other direction. And because that rotation is clockwise, we're going to call that a negative moment. And so the sum of all these moments created by those four forces adds up to 0. So I'm going to write equals 0, okay? So the first thing I'm going to do is, since this part's the only negative one, I can actually add that to itself, and that's going to bring it over to the other side of the equation. So I'm moving the 20 times RA to the right side, and so that's going to give me 20 RA equals, and then I'm just going to do all of this stuff, and that will be on the other side of my equation. So in my calculator, I have 1,000 times 15, that's this moment, plus 4,000 times 10, plus 3,000 times 5. And so all of that gives me 70,000. So I've simplified all this. We have 20 times RA equals 70,000. And if I divide both sides by 20, that's going to solve for the final answer. So the reaction force at point A is, and I can drop a couple of zeros, so I have 7,000 divided by 2, that's 3,500 pounds. And so that means this reaction force that's holding the whole bridge up when it's being pushed down with all of these forces is equal to 3,500 pounds. And because I got a positive answer, that tells me that when I assumed this reaction was pointing upward on my bridge, I was correct to assume that. So I'm going to draw a little upward arrow to remind myself that yes, this is in the upward direction. It's holding the bridge up. And that should make sense because all of these external forces are downward. So there should be a force holding the bridge upward at that reaction. Now that I've solved for one of my three reaction forces, I'm ready to use the other two equations of static equilibrium to solve for the next reactions. Okay, so I think I'm going to move on to this equation, and that tells us that the sum of all forces in the x direction equals 0. And if you look at our bridge here, so going back to the bridge, There's only one force in the x direction, and that's RCX, because there's no external horizontal force on this bridge. So this is my only force in the x direction. And that means that I have RCX equals 0. And so this is a very easy one because there is no external x force. That means that there is no reaction at point C in the x direction. Very, very simple one. And now we can do sum of all forces in the y direction equals 0. And so for this one, we're just adding up all the forces in the y direction. We have RCY, so this unknown reaction force here. And then we have the 1, 2, 3 external forces that are all pushing downward. And so what that gives us is RCY, which is positive because it's pointing upward, minus 1,000, because that force is going down, which is the negative direction, minus 3,000, because that's also a downward force, and minus 4,000, because again, that's also a downward force. But we also have this RA, that reaction on the left side of the bridge, that's 3,500 upward. So we have plus 3,500. All should equal 0. The sum of all forces in the y direction equals 0. So we have RCY, and then I can just add all these forces to the other side of the equation to move them. So we have 1,000 plus 3,000 plus 4,000. And since this one's positive, I'm going to subtract it to get it to the other side. So minus 3,500. And so now I can just solve for RCY. So the reaction at point C in the y direction is equal to, that's 4,000 plus 4,000, that gives me 8,000 minus 3,500. So I get 4,500. So this reaction force at point C in the y direction is 4,500 pounds. So if I go back to my diagram, this is where I like to replace all of these unknowns with the new values that I've discovered. So remember, we said that there's a 0 pound reaction in the x direction at point C. So I'm just going to get rid of this because there really isn't a reaction force there. We said that there's a 3,500 pound reaction at point A. So I'm going to replace this on my diagram with 3,500 pounds. And it is upward because I got a positive answer that verifies that it's in the upward direction. And then I also got 4,500 pounds at RCY. So this reaction is now known, and it's 4,500 pounds also in the upward direction. So basically, all of these external forces pushing down has caused these two reaction forces at the supports to push back up on the bridge, but they are unequal reactions, right? It's not symmetrical because if you think about it, there's more force on the right side of this bridge. There's the stronger forces on this side. So this support has to do a little bit more work to hold the bridge up. We have now successfully found our two reaction forces for our truss. So when these three external forces push down on the bridge, the two supports react by pushing up with 3,500 pounds on the left support and with 4,500 pounds on the right support. So now please stay tuned for part 2 of this video, which is actually linked in the description for this video. And in part 2, we're going to go over the joint by joint analysis to actually finish this problem and figure out how much tension or compression is inside every single member of this bridge. Thank you for watching Fantastic Physics. Please like this video and subscribe to our channel if you want to see more interesting physics content. Goodbye for now, and remember, it's a fantastic universe out there, so stay curious.